Hello. All right, let's get started. Is there any questions? Any questions? Any questions? All right, then. A big part of this class is about linear equations and its neighborhood applications, word problems based on linear equations, and you can go in all kinds of directions. Actually, we have two such topics today. The first one, it's kind of straightforward application of one-step equations. I don't want you to be misled by the title. The title is basic percent problems, but the word basic is misleading. These can get pretty tricky. So first we're gonna do basic fraction problems. And by the way, if you already have a method that works, and by works, I mean you can solve problems and you get the correct result, then don't worry about this. But there is gonna be three types. All right, so let's make what is 3/4 of 60? Exactly. 1/4 of 60 is 60 over 4, 50, 15, and then 3 times that is 3 times 15, that's 45. Also, you can just multiply the two and we get the same thing. So I'm gonna say something. 3/4 of 60 is 45. And this is a little drama with three completely different actors. If you think about the statement 2 plus 3 equals to 5, then 2 and 3 are pretty much, they have the same role. This is three different characters here. And so there are gonna be sort of three type of basic fraction problems based on, I'll give you two and ask for the third one. This is type 1. Type 1 is like the most straightforward, find a certain fraction of something. But for the other two types, then, well, for this, I gave you these two and withheld and asked for this. But we can ask, I can give you these two and ask for this, or these two and ask for that. That's the three types. So before we do anything, I want to develop a language. And again, if you already have your method, don't worry about it. But just to name these characters, this we're going to call the fraction. Well, that makes sense. It looks a lot like a fraction. This is going to be called either the base in other languages, or we're going to call it the of number because the word of is always nearby. And we're going to call the is number. This is not a very pretty language. And so just so you know, this is going to be a sort of an application of one-step equation where you can have one formula and you can use it in three different ways. So the one formula that we're going to use is the following: is fraction times of. That's the one formula you have to memorize. Is fraction times of. For example, in our example, fraction is 3/4 times 60 is 45, right? 45 is 3/4 times 60. Now let me show you how it translates to practice in type 2. So type 2 would be something like 18 is what fraction of 48? And so here's what I want to avoid. I want to avoid to say, okay, when the problem is do this, 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 and that. I don't want to give you meaningless algorithms to memorize because those are the things that you're not going to remember it a week later. So I want to give you something that's a little bit more meaningful when you have to memorize one thing and the rest you sort of figure it out. So is fraction times of. So we have to identify two of the numbers given and the third one is x. We have to fill out this table with this sentence. And usually 2 out of the 3 is pretty easy. Do you see something that you can easily identify? So what I'm trying to ask you is fill out this table based on the problem. Who is this 18 or 48, or who is the fraction, who is the odd number? Usually 2 of the 3 are easily identifiable, and the third one is the third one. 18 is this number. The word is really close by. Very good. What else? Well, the what fraction, I would call that x. That's the one that we're asking, and the of number is 48 because the word of is nearby, right? So here is what we're going to do. We're going to rewrite this statement, but we're going to sort of replace is with 18, f with x, of with 48, and then we're going to solve for x. It's at the worst case scenario, it's a one-step equation. So is fraction times of means 18 equals x times 48. And now look at it, it's a one-step equation. We're going to solve for x by dividing both sides by whatever is multiplying x. And then remember, x has to be a fraction. It is already a fraction. All we have to do is reduce it. I'm seeing 6. 18 is 3 times 6. And 48 is 8 times 6. This is how you're going to simplify fractions in the future, 3 over 8. So the answer, we think 18 is 3/8 of 48. Now, checking is always type 1. So to check, let's find 3/8 of 48, and it better be 18. Well, 1/8 of 46 is 1/8 of 48 is 48 over 8. That's 6, and 3 times 6 is 18. So it looks like we did it right. Any questions? Now, type 3 is probably the most exciting. When the odd number is withheld and asked, and the other 2 are given. So something like 3/7 of a number is 24. Find this number. So is fraction times of. Let's identify 2 numbers and 1 x. Who goes where? Is this 24? We have our is department. Good. I think the fraction is pretty recognizable too, right? The fraction, the one that looks like a fraction is a fraction. And then you can check, oh, of a number, find that number. So the of number is being asked. Yep, exactly. So now we state the same equation, the same formula, and then we solve the equation for x wherever it is. So is fraction times of, and we're gonna solve for x by multiplying both sides by whatever is multiplying x. So we're gonna divide both sides by 3 over 7. So x is 24 divided by 3 over 7. And remember, to divide is to multiply by the reciprocal. I know we just did that, so 3 over 7, 7 over 3. Cancel, 8. 8 times 7, 56. Over 1, that's 56. So we think it's 56, right? To check, take 3/7 of 56. It should be 24. And it is, right? It's 3 times 8. Any questions? All right. So these are the 3 types of basic fraction problems. And now we're going to repeat these problems, but now they're going to be called basic percent problems. So basic percent problems. Type 1, find 40% of 300. That's type 1. You don't really need an equation for that. The equation is kind of solved for x already. Yeah, so we're looking for 40 hundredths of 300. 100 is 3, and 3 times 40 is 120. Very good. Okay. Now here is a type 2. A type 2 is, these things are gonna get interesting pretty quickly. And again, the word basic should not fool you. This can be tricky depending on what kind of numbers show up. So your teacher has to know what they're doing. Let me see. 24 is what percent of 400? So it's not tricky if it's just when we get the fraction at the end, how do we convert it into percent? This one is going to be nice, I think. So is fraction times of what percent means that the fraction is being asked, and we have to present it with a denominator of 100. 24 is the is number, 400 is the of number. So is fraction times of, so for x. And now comes the cute part. We have this instinct of reducing it, but now we shouldn't reduce it. We are asked for what percent, which means the answer should be a fraction with 100 in the denominator. So the slickest, smartest thing to do is just divide upstairs and downstairs by 4. Because that's the quickest way to get to a percent, right? So x is 6 over 100 is 6%. Now, this is where you have to be lucky. If we have a fraction like 3 over 7, that's nasty. Actually, I can. So one question that comes up here is, how do we convert a fraction to percents? Well, there are 3 cases. Case 1. Suppose you get something like 3 over 5. What percent is 3 over 5? Write it as a percent. Exactly. So we're gonna, so case 1 is when the denominator is a divisor of 100. Then we just have to scale it up. Easy breezy. So when it keeps, expenses are killing me. I feel them every morning and they drive me crazy anyway. So it's when the denominator is a divisor or factor. And then it's easy. We just multiply upstairs and downstairs by a suitable number. What number? The one that takes the denominator to 100. Okay. Case 2, you just have seen case 2 when the denominator is a multiple of 100. Even then, it should be a nice multiple. Let me give you an example when it's not very nice. Something like 3 over 700 is not nice, because what's wrong here? To get to a percent, you would have to divide both upstairs and downstairs by 7, and the top is not really divisible by 7. So I'm just going to fix it for now. This here is what percent? What percent is this? Come on, pumpkins. No. 35 over 700. Express this as a percent. Exactly. There we go. To to get to the denominator. So 1 over 20 might be true, but that's not what we need. I didn't say reduce to lowest terms, but I said write it as a percent. So that means the best way would be if you divide it upstairs and downstairs by 7, and then we get 5 over 100, which is 5%. But the third case is when numbers just don't compose. And I'll try to keep it between these two, but sometimes the numbers just don't cooperate. Just happens, especially with interesting stuff that's coming your way. So case 3, numbers are not nice. Numbers are not nice. Once I was asked to sit in another teacher's class because the students were complaining about this teacher, and he was truly, truly terrible. I'm sorry to say that. He was just god awful. The students were confused and frustrated, and they kept asking. And the thing was about to convert between decimals and percents. And they kept asking. The students were very engaged. And the teacher said, oh, that's easy, just multiply by 100. Oh, that's easy, just divide by 100. But there was no, like, okay, but when do we do this? When do we do that? It was just so sad. Like the teacher, in a way, was clear, but very unhelpful. So you have to understand, I'm trying to do the opposite of that. So if you already have an easy way, don't worry about it, keep it. But so if the numbers are not nice, go from fraction to decimal using the calculator. And then we're gonna grow a 1 and convert to percent. I'll show you, convert to percent. So let's say we have a truly, truly terrible fraction. How about 3 over 7? You cannot scale it up or down. This is not, 7 is not gonna turn into 100, not from multiplying it by integers or dividing, right? So here's what we're gonna do. I know it's ahead of our time. I think it's going up a little bit. No. Okay. So just express it as a decimal. Don't worry what it means. I mean, the teacher before me was supposed to worry about that, but we should make time for a class on decimals. Okay, now it's a terrible number. What do we want? We want a fraction with 100 in the bottom, and then we're going to break it down to 2 projects. Okay, let's make it just a fraction, and then this is sort of trivial. This is what I call growing a 1, right? You can always look at a fraction as a division problem, and if you divide something by 1, you're not changing its value. And now it's a fraction with a nicer denominator, and we can multiply upstairs and downstairs by 100 now. So we multiply upstairs by 100, downstairs by 100. Now you should know, but if you don't, if you use the calculator, if you multiply a decimal by 100, all we're doing is moving the decimals, because a 10 will be promoted to be 100. 100 will be promoted to 1,000. Of 1 over 1,000, when you multiply it by 10, you're just promoting it to the next. So when I'm going to multiply this by 100, the decimal is going to just climb after the 2. It's just going to move up. Times 100. There it is. And just copy. There. That will always work. There is just one little catch. Whenever you have these terrible decimals, people will ask you to round. Like don't go to 43. 43, that's really gross. Usually, my open math will give you some instructions. It will say up to 3 digits after the decimal point. That's called 3 decimal places. But notice that because of the moving of the decimal inside the problem, you have to keep 5-digit precision so that at the end you have 3-digit precision. So that's a little. So that's how you do it when things are the worst case scenario. Okay. Any questions so far? And so here, you never have to ask yourself whether you multiply or divide by 100. We're going to grow up. It's kind of something to remember that is meaningful. And meaningful things, understood things, are easier to remember than random things. Try to memorize a word like table or a random sequence of 5 letters. The random sequence of 5 letters is much harder to memorize. Okay. All right. That was type 2, and then type 3 is when the off number or the base is withheld. Okay. So 14% of a number is 420. Find this number. I want you to use your common sense and sort of your numerical sense. Like 14% is close to 10%. That's like 1/10. This should be a bigger number. This is about 1/10 of a number. So it should be around 4,000, what we're looking for, right? So no one is asking you to find something like 42. We're going up, in fact. Find this number. Sometimes you would see something like 14% of what number? This is 2 different phrasing of the same question. And then we're going to go is fraction times of, who is who goes where? F is no. Look, the percent is a fraction. So the percent has to be the, unless things are very tricky, very strange. So I agree the is number is 420, but the fraction is 14 over 100. And it is the of number that was withheld and asked. Of a number that we have to find. Of what number? So whenever you see percent in that problem, it's probably the fraction. And so is fraction times of, is fraction times of, and you feel free to use the decimal. That's why percents are so nice, because the denominator allows for the numbers to be easily written as decimals. It's basically the kind of fraction that's well aligned with our decimal system. 14 over 100 is nicer than, say, 14 over 3. See, that's nasty. But 14 over 100, again, we just demoted all digits by, see, if you mentally move it back. And then, so feel free to use it as a decimal. That's the nice thing about percents. 1/3 as a decimal, don't do it. You're going to lose precision. It's harder to write. Percents, nice as decimals. We solve for x. So we're going to divide both sides by 14 over 100 or 0.14. I'm just going to keep it as fractions for that. So x is 420 divided by 14 over 100. Next year you have a big bar because the order does matter. And so to divide is to multiply by the reciprocal. So we have 420 over 1 times 100 over 14. And that's going to be a big number. 3,000? Did you get 3,000? Because 42 is 3 times 14. I know that. So 420 divided by 14, that should be 30 times 100 is 3,000. Okay. Very good. Any questions? Things will get pretty tricky pretty quickly. Type 1, actually, they're all interesting. And so first of all, a lot of the time, the problem becomes trivial if you can boil it down to a question like 14% of what number is 420, or find 35% of, so those are basic questions. You will see very quickly what I mean. And sometimes to solve a problem, you have to do several, one of them, and you have to one who comes up with it. For example, let me ask you two questions. Okay. 50 is what percent of 250? And 50 is what, these are type 2, what percent of 200? I'm not asking 50% of stuff. The percent is missing. So we took a certain percentage of 250 and the result was 50, not 50%. But at least, as I said, at least she's talking to me. So let's see. No, that's all right. It's okay. I'm exhausted too. It's the daylight savings and other stuff. That's okay. As long as you talk to me, I don't mind. So for the first one, we're gonna say is fraction times of. The is 50, the fraction is asked, and the of is 250. So is fraction times of. So for x, it's gonna be 50 over 250. Now that's interesting, because 250 is neither a divisor nor a multiple of 100, but still it's nice because we can get rid of, we can divide upstairs and downstairs by 5. Then this is going to be 10 and this is going to be 50, which is now nice. Now we can, so it's scale it down and then back up, which is 20 over 100, which is 20%. In general, 1/5 is 20%, right? But we didn't have to go that far. Okay, so the answer to this one is 20%. Now 50 is what percent of 200 is an identical problem. It's just the numbers are. So this is not the excitement. This is just getting ready for the excitement. Is now still 50. The fraction is still what we're asking, but the of is now a smaller number, 200. So it should be a higher percentage. Now we have our percentage department. Excellent. So is fraction times of. So for x, we get 1/4, which is indeed a quarter is 25 cents, right? 50 over 200. But we're just going to divide both sides, both upstairs and downstairs by 2 because we're going for a percent. So x equals 25%. All right. Now, we raise the price of an object from $200 to $250. What percent of a change is this? 20 or 25, right? What percent of a change is this? You see why this question is, it's not difficult, but there is something going on here. Well, what do you mean? Well, 50 is 25% of this and 20% of that. Which one do we use here is the question, which is not really a math question. This is a matter of convention. Do you know which one we use in case of changes? So you see there are two numbers here. There's 200 and 250. And the number 50, which is the change between the two, is 20% of one of them, 25% of the other. What's the convention? Are we always comparing it to the smaller one, to the bigger one? Or Monday, Wednesday is the smaller, Tuesday, Thursday is the bigger? What's going on here? So here is the convention. Whenever you have a change, and you want to say what percent of it, we always compare it. The of number is always the original one. So not the smaller, not the larger, the chronologically earlier one. So in this case, if we, and this is the interesting thing, if we go from 200 to 250, then we must ask, $50 is what percent of the earlier one of 200? And the answer is 25%. So going from 200 to 250 is a 25% increase. But going back from 250 to 200 is a 20% decrease, right? Because now if you go from 250 to 200, now this is the new original, even if it's a full circle. Imagine that someone raises the price from 200 to 250. That's a big, steep increase of 25%. If you change your mind and you want to go back, it's not a 25% decrease that you need, because now we're talking about a bigger number. It's actually, in this case, it's a 20% decrease. So things are getting interesting a little bit, right? All right, so let me give you an example when you're going to have to have initiative and ask those questions yourself. Now I'm going to hold your hand, but not for long. So in percent world, 20 plus 30 is not 50. All right, so let's grab a nice amount, increase. Okay, so let's make it divisible by 100, so we're not dealing with fractions. Increase 5,000 by 20%. So that has two parts. Find 20% of 5,000 and add to it, right? You do it. Increase 5,000 by 20%. That's a type 1, right? What's up? Did I lose the internet? No one is talking, no one is chatting. You guys are still here, right? Okay, so, okay, good. So 1,000 is not the result. Okay, 1,000, now add it to 5,000. So the result is going to be 6,000, right? Because it's 5,000 plus 20% of 5,000. We just discussed that 20% is just 1/5. So that's 5,000 plus 1,000, which is 6,000. Okay, number 2, increase 6,000 by 30%. Okay, so the 3 of you are here, the other 2, other, yeah, ladies are here. So increase 6,000 by 30%. What do we get? So find 30% of 6,000 and then add it to 6,000 and then tell us. Oh, I forgot to check. Yes. So we're gonna do 6,000 plus 30% of 6,000, which I think is 6,000 plus 1,800, right? And that's how we get 7,800. Okay, good. So this is what I will refer to 2 consecutive changes. We took a quantity, we increased it by 20%. And then what we got we further increase it by 30%. And what I'm going to show you is that as a single change, it's more than 50%. So now, here is the third question. What is the change? What is the total change? We went from what to what? So what is the difference between the first number and the last number? No, from the first number. So we're going to analyze. What we're going to do is we're going to look at two consecutive changes, and we're going to express it as a single change. So we started from 5,000, then we went to 6, then with 7,800. So 5,000 to 7,800 is 2,800. And now here is the question. 2,800, the change, is what percent of the initial number, 5,000? So basically we're asking, okay, so going from 5,000 to 7,200 in one big swoop, 78, not 72, right? 78. So this as a single change is what percentage of a change is, which is the same thing as asking 2,800 is what percent of 50,000. And it's clearly more than half, right? Half of 5,000 is 2,500. This is more. 56%. So in percent world, so is fraction of is 5,000, x is fraction of x, wrong way. Oh, how about just 1 0? We're going for a person. So x is 2,800 divided by 5,000. But if we chop off 2 zeros, then it's 50. So we multiply upstairs and downstairs by 2, and that's 56 over 100, or 56%. So in percent world, 20 plus 30 is 56. Can you explain why this is happening? Why did we get more than 50? No, I don't think it's because, okay, if you fix a number, let's fix a number 400, then 20% of 400 plus 30% of 400 is 50%. The trick is that we didn't take 20% and 30% of the same number, right? The second one is 30% of a bigger number, which is a bigger percent. I assume 36%, right? So the trick is that the second increase, 30%, it wasn't 30% of 5,000 like this 20% was. It was of a higher number, right? That's what causes this trickery. But here is the thing. This answer, this 20 plus 30 equals 56, does not depend on the starting value. So what if I just ask you something like this? Express a 20% increase and a 30% increase and a subsequent 30% increase as a single change. Then you have to come up with these 4 different problems, right? First, you have to have the initiative to say, I'm going to grab a number and make it divisible by all kinds of things, including 100, to make your life easier. And then increase it by 20%, then increase it by 30%, and then look at the change. You see, it's not a difficult problem. It's more like 5 easy ones. Okay, 4 easy problems, right? You do a type 1 to perform the first increase. You do another type 1 to perform the second increase. Then you subtract to get the change. And then there is a type 2 to express the change as a single percentage. And these things are not obvious, right? Here is another thing. Let's start with this 5,000 again. Start with 5,000. And here is what I want to do. We're going to increase it by 20% and decrease it by 20%. Do you think we're going to get 5,000, more than 5,000, or less than 5,000? So first, we're going to increase by 20%, then decrease by 20%. What do you think? What is your hunch? We're going to solve this. It's not going to be, you know, it's a type 1, and then a type 2. But just what is your hunch? Are we going to get 5,000 back, more than 5,000, or less than 5,000? Oh, come on, I'm asking you to guess. Okay, we have a guess. Good. And thank you for talking to me. But let me remind you that when we went from 200 to 250, going back was a different percentage, right? So chances are it's not gonna be like that, but at least you're willing to talk to me and willing to take a chance. All right, but let's let the numbers sing their song. So you just have to keep track of it. It's sort of just do research. Let's increase 5,000 by 20%. Didn't we just do that? So 5,000 increase, that's when we got 6,000, right? Increase by 20%. 20% is 1/5, that's 1,000, added to 5,000, so we get 6,000. We did this already. Good. Now, decrease 6,000 by 20%. So we went below 5,000 because the second decrease was based on a bigger number. The second decrease was bigger than the increase was before. 6,000 minus 20% of 6,000 is 6,000. That's 1/5 minus 1,200, right? Equals 4,800. Okay, so we landed on less than 5,000, but just for kicks and giggles, well, we have to express it as a single change. So now the question is, going from 5,000 to 4,800, what kind of a change is this? And when I ask what kind of a change, you have to give a number and increase or decrease. This is clearly going to be a decrease, but what percent of a decrease is this? What percent of a change is this? Oh, you're doing something. You know what? You got the right number. I don't know what you did. You do something faster than what I'm doing, but good. You just didn't interpret it right. What you got is, oh, you said 4,800 is what percent of 5,000. Let me tell you something. This number is 96% of this number. So what we have endured is a 4% decrease. That 9.6 is really 0.9. So you have to interpret your number correctly. So I was hoping that you're going to say, okay, that's a $200 loss. I mean, a 200 loss. And we have to ask 200 is what percent of 5,000. And so this is what I mean by make it boil down to basic questions like that. And once you have those questions, it's pretty straightforward. The hard part is to make it boil down to a question like that. So is fraction times of is 5,000 Is this 200? Asking about the fraction. So is fraction times of. So x is 200 divided by 5,000. We chop off 2 zeros, we get 2 over 50. So that's 4 over 100, and that's 4%. Now, what you did is I'm withholding as a slick shortcut. Instead of subtracting the 4,800 from the 5,000 and asking what percentage of a change is that, we can ask, okay, the new quantity, 4,800 is what percent of 5,000? And when we solve that problem, the answer is going to be, it's 96%. And now you have to do the subtraction. Okay, we started with 100%, we landed on 96%. So what's the difference? Right? These things get pretty interesting. So we can say 5,000 minus 4,800 is 200, and then 200 is 4% of 5,000. It's first a subtraction and then a percent problem. But we can do first a percent problem. 4,800 is what percent of 5,000 is 4,800. Fraction is x, 5,000 is the of. And so is fraction times of. So for x, so we chop off 2 zeros and then double. We get 96 over 100, which is 96%. And now we do the subtraction, right? Okay, so we went from 5,000 to 4,800. 5,000 is actually 100% of itself, right? And we just figured out that 4,800 is 96% of 4,800. So the change is a 4% decrease. Right? But I often see people getting 0.96. They're getting the answer as a decimal, 0.96, when they ask, okay, this new condition is what percentage of the old condition? And then they think that they're not looking at the change, they're looking at the result as 96%. But then they say, oh, it's 9.6% because that makes sense size-wise. But it's pretty interesting. Is there any questions for those few of you who are still here? And then there are lots of interesting questions like, okay, so here is what we found. In percent world, 20 plus minus 20 is minus 4, right? Basically, if we do 2 consecutive changes, a 20% increase and then a 20% decrease, there's going to be a 4% loss because the second change is based on a bigger number. The of number here is bigger. So there are all kinds of questions. The first one is, does it matter what number we start from? As it turns out, no. But the other interesting question, what if we swap the order? What if we start with a decrease and then an increase? Are we going to get a different answer? Maybe then we're going to overshoot. What do you think? What if we swap the changes? First decrease by 20% and then increase by 20%. And don't compute, just try to think first. I just want you to guess. No one is going to point and laugh. No one has been doing that. You're right. But you can see that, right? Okay, so we do the decrease and then the 20% of a smaller number is not going to take us back to the same place. In fact, we're going to get the same number. The order doesn't matter, which might be a good thing. But you see, when I ask you about expressing 2 consecutive changes as a single change, you have to break it down. You might have to make up a quantity. You're going to have to be proactive and organized. I'm not going to hold your hand for long about these pretty little questions. So start with 5,000, then a 20% decrease. I think it's going to get us into 4,000, and then 4,000 and a 20% increase is gonna be 20% is 1/5. That's 2/10. That's 800. So we go back to 4,800, which is the same thing what we did before. So not only it's gonna be less, but it's the same amount. And it's kind of interesting if you think about it, just kind of logic it out. Like, okay, we have, if we do an increase and a decrease of the same amount, after the increase, we take the same percentage of a bigger number, so we're gonna get that. And then if you do the decrease first, then what we're adding back is gonna be too small to match us. So interesting stuff. Interesting stuff. And then another question could be, oh, right, so we increased by 20%. If we go right back where we came from, what percentage of a decrease would that be? I just want to warn you, that's where it's nearly impossible to get nice numbers, because one of the two is, there is this example of 20 and 25, and that's the only nice pair. I'll just, anything you can come up is going to be a bad, one direction, you're going to get a bad number. So the question is, all right, let's say we increase. So let's say we grab our 5,000. And let's say we increase it by, let's say 10%. If we want to go back to 5,000, what percentage of a decrease it's going to be? And it's not going to be 10%. You can think about, is it going to be less or more? To go back to 5,000, what percent of a change do we need? All right, so first increase 5,000 by 10%. That's 5,000 plus 500. Oh no, yeah, it's 5,500. Okay, to go back, we have to go from 5,500 to 500, 5,000. So we have to ask 500 is what percent, and why it's going to be a disgusting number is this is going to be the off number now. 500 is what percent of 5,500? This has to do with, it's very rare that both a fraction and its reciprocal are nice with respect to 100. This is going to be nasty. All right, so we ask 500, and this is the key to come up with questions like this. Then the answers are easy. So the is 500, and the of is 5,500, and the fraction is what's asked, and is fraction times of, oh, I'm sorry, fraction is x. Now, if we chop off 2 0, you see 55, that's not going to be pretty. So what I recommend is that thing, go into a decimal, grow a 1, and then, so 5 over 55 is not as pretty as 55 over 5. So 5 divided by 55 is going to be not nice. So x is, and then if it's approximation, we start to wiggly, like approximately equal, not exactly, is 0.090990. Interesting. Basically, you don't have to know this, but this decimal goes on forever and ever and ever. 909090. It's just this 09 was rounded up to a 10. That's just a rounding. But that's okay. 0. No, it's a 91. The 09. Okay. So what I told you is to grow a 1, and then multiply upstairs and downstairs by 100 to get to a percent. So that's, and you can use the calculator, but it's 9 and change. It's not 10%. Backwards, because we're talking about the bigger number, it's slightly more than 9%. So it's 9.091%. So I'm warning you, it's very rare that both upstairs and downstairs is an integer. It just cannot be done for most numbers. Any questions? All right, so there is plenty of dirty tricks that is left untapped here. There's lots of interesting things that will come out. We're not done with basic percent problems. This was just our first little encounter. Now you're gonna do homework, you're gonna think about it, and then we're gonna go further. So now for some other topic. It's another sort of application of linear equations. And I'm already warning you about complicated solution sets. Okay. So here is an equation in 2 variables. So a solution is an ordered pair of numbers. Well, by ordered pair of numbers, you cannot just give me 3 and 4. You have to say one of them, X is this, Y is that. So an ordered pair of numbers that make the equal statement true. Excuse me. There's one more coming. Okay, so the thing about it is this one will have infinitely many different solutions. For example, how about if Y is 1 and X is 5? X is 5 and Y is 1, right? Because 5 plus 2 times 1 is 7. But this is not the only one. And when it's X and Y, we usually alphabetize them and we say, okay, 5, 1. That's less writing than this. Come up with other solutions. There are infinitely many. That's the problem. Come up with a pair of numbers so that if we substitute one of them into X, the other one into Y, the other side will be 7. I'm pretty sure you can all do this. 3, 2 will work. X equals 3 and Y equals 2 will work because 3 plus 2 times 2 is 7. Excellent. Actually, here is a sleazy little trick. Just come up with any number for Y, put it in there and sort of solve for X, right? That's why it's an application of what we have been doing. So don't start with X, start with Y. What if Y is 3? What if Y happens to be 3? What should X be then? Yeah, X equals 1 and Y equals 3 will work because 1 plus 2 times 3 is also 7. But it's also going to work if Y is too much. If Y is 10, then we just need to solve X plus 2 times 10 equals 7 for X, right? Come on, you cannot solve this equation for X. Exactly, so I didn't tell you. Y equals 10, that means X should be negative 13, because indeed negative 13 plus 2 times 10 is 20 minus 13 is 7. So here is the problem. There are several problems here. There are infinitely many solutions. But we cannot say something like, we cannot express this solution set as x could be any number and y could be any number, because 5 and 5 is not going to work, right? X equals 5, y equals 5 is 15 is not 7, right? So there are infinitely many solutions, but there is some sort of a relationship between them established by this equation here that we somehow meaningfully we are trying to express. Like, how do we write down how do we express meaningfully these solutions? I already told you that there are infinitely many solutions, but it's not true that every pair of number would work. In fact, what's going on is that you pick any number for y, and there is just one that will work for that x, right? You can pick x too, but here is my problem with x. If you pick x equals 0, then you have to divide. Now you have 7/2, right? 0 is just the easiest thing to substitute. Y equals 0 would give you x equals 7, right? So y equals 0 gives you x equals 7, and x equals 0 will give you 7/3, right? X equals 0 will give you y is 7/2, 3.5. So here is the thing, especially when you see the letters x and y and not say p and q. So if you see something, not something like p plus 2q equals 7, but something like x plus 2y, and think about graphing. What if we started to make points out of these? And then what you will see, it's really, really meaningful. So if you start plotting, let's start plotting these points. So our first pair that was my example, 5 plus 2 times 1. So if x is 5, then y is 1. And then if x is 3, then y is 2. And then if x was 1, y was 3. If y was 10, x is off the picture, but it's somewhere here. Okay, if x is 7, y is 0. If x is 0, y is 3.5. I'm sorry, it's kind of hard. If x is 0, y is 3.5. Do you see something going on here? Find more solutions. Find something with something here. Find some solutions here. -2, -5, I don't think so. -2, -5 is not going to give you +7, right? But again, at least she's talking to me. -2 for x, I think it's 11. So -2 plus 2 times y equals 7. 2y is 9. Y is 9/2. That's 4.5. So if x is -2, y is 4.5. You know how I knew that that cannot be? Because this thing is going to form a line. And -2 -5 was just way off to fit on this. This is going to be a straight line. So it's a really meaningful way to represent this strange solution set by graphing it. In fact, the graph, so here is an equation. X plus 2y equals to 7. And what's new here is that we have two variables. -1,4 sounds right. -1,4 sounds perfect. Find something here. And by the way, you can start with x equals 7 or y equals 7. Y equals 7, what should x be? Y equals 7. Oh, the equation is here. So I think it's easier to start with y because then you don't have to divide by 2. It's just another sleazy little trick. If y is 7, what should x be? And it should be somewhere here. So my question is, if y is 7, x is what? And what you have to do is take y equals 7, shove it into that equation, and then it's an equation you can solve for x. -3.5 sounds right. Yep. Exactly. This point is off. You see, these graph papers are lovely. Don't use things that you draw. There is a lot of structure in the fact that these are even grids. Okay. Now we just graphed. Oops. Oh, I shouldn't have used that one. We just grab 1, 2, 3, 4, 5, 6, 7, 8, 9 points, but every point on this line is part of the solution. So equation equal is, I'm just going over to, 2 to the left, 1 up, 2 to the left, 1 up, 2 to the left, 1 up. Yeah. So you sort of decode it. This is what keeps a straight line straight. That you can go 2 to the left, 1 up, 2 to the left, 1 up, 2 to the left, 1 up, to the left, 1 up. Very good. So the graph of the equation x plus 2y equals 7 is the set of all points pxy such that x plus 2 times y happens to be 7. And so what's going on is that there is exactly 1 y for every x, there is exactly 1 x for every y. And the most meaningful way of expressing it is variations on this line. But every point, even like ugly, disgusting points, I mean, points with ugly, disgusting coordinates, those two coordinates also form a solution for this equation. Yeah. The way to make it a little bit shorter is to say pxy such that x plus 2y equals to 7. But people will just say graph x plus 2y equals 7. They will just say graph this. Now, I think I already talked about linear things. Remember, quadratic meant of degree 2. Now, linear means of degree 1. But look at the word line, it's carefully hidden in there. Because degree 1 things, when you start plotting them, they will form straight lines. Straight line, linear, same thing. There are 3 types of linear equations. Yeah. So there are 3 types. There are 3 types. 1, linear in x and y. That's what we did just now. 2, linear in x. That means y is not present. Something like x equals 3. But I'm telling you that x equals 3 is short for pxy such that x equals 3. And when we graph that, okay, it could be a little bit more complicated, like 2x plus 5 is 11, but then you solve for x and you get that, right? If it's linear in x only, then basically you can solve for it. And then x equals 3 means, well, any point on the coordinate system where the x coordinate is 3. So that means y is not even present. That means it doesn't matter what y is, x is always 3. So the way that will look is x is 3 even if y is 0. Here is 3, 0. X is 3 even if y is 10. X is 3 even if y is 5. So And every point will work as long as the x coordinate is 3, and that's going to be a vertical line, like so. Just think about it this way. I want to do Chicago talk. Where are all the buildings with north address 500? How would you describe all the houses with north address 500? And what I'm hoping that you're going to say, oh, it's a east-west street, right? At a fixed north. I should have said west 200. West 200. This is east 300, I guess. The east address is 300. So that's when linear in x only. And linear in y only, you might have a linear equation in y only, but then you can solve for y. Something like 5y minus 1 is 29. 5y is 30. Y is 6. And that's going to be a horizontal line because no matter what x is. So this is confusing when people say graph this. Graph y equals 6 is short for graph the set of all points p, x, y such that the y coordinate is 6. And that's a little cleaner. That's a little bit more clear. So the equation of this line is x equals 3. And y equals 6 would, you guys deserve the best. Y equals 6 would look like this. If x is 0, y is 6. If x is 5, y is still 6. If x is 6, y is still 6. Y doesn't care. For every x, y is 6. That's what that looks like. But most of the lines will have equations linear in x and y, and they will be and everything in between. They will be the ones that I guess tilted whenever you have some x and some y. Any questions? Okay, so why is this an application of linear equations in one variable? Because when we are asked to graph, now as long as it's linear in x and y, it's kind of symmetrical. So you can come up with any value of x and solve for y, or any value for y and solve for x. You should pick the one that's easier for you. We can pick any value of x, put in the equation and solve for y. And rinse and repeat. Put in the equation and solve for y. Or pick any value of y and solve for x. In this case, I think this was easier. It's not a big deal to divide by 2, but you don't have to if you start with y, right? Let's say y equals 4. 2 times 4 is 8. Negative 1 will make it right. So if y is 4, then x is negative 1. But then we can turn it around and say, well, if x is negative 1, y will turn out to be 4. Or pick any value of y and solve for x. But the entire graph is, we have finite life, finite time, finite paper. So we just find a few points, and understanding that it's a straight line, we just put the ruler through and. All right, let's see an example. Another one. So you're not going to be able to show me your paper, although I told you should buy a document camera. So you're just going to have to tell me solutions. Okay, find points. Let's say 3y minus x equals 4. Give me points on the graph of this? 5, 9. Let's see. So 5, 9, that means x goes into 5, 3 times 9. Oh, you mean 9, 5, right? 3 times 5 is 15, minus 9 is 6. You must mean 11, 5, no? So 5 and 9 will not work because 3 times 9 plus minus 5 is 22 and not 4. You meant 3, 5. So yeah, so I think sometimes it's easier to come up with y and solve for x, but when you present, always x has to come first. So it's not logical, it's alphabetized. So 3, 5, you say, well, at least you're talking to me. 3, 5. 5 times 3 is 15, minus 3 is not 4. Okay, 5, 3. We'll get there. We'll get there. Yeah, it's basically, you just brute force it. Grab one of your numbers. Are you starting with x or y? And then shove it in there, and now there is an equation in front of you, solve for the other unknown. Oh, I try to make it different. It's very similar to the previous one. So again, check this out. If x is 0, 1, 2, 3, 4, 5, then we have to solve for y. Solve for y in 3y minus 0 equals 4. That's 3y equals 4. That's going to be a nasty little surprise. That's a nasty number. Or 3y minus 1 equals 4. Solve for y. Or 3y minus 2 equals 4, right? For every value of x, you have an equation for y that now you can solve. 3y minus 3 equals 4. 3y minus 4 equals to 4. 3y minus 5 equals to 4. So, but what's better is, you see, you're always dividing by 3 at the end because of this 3 here. So actually, I would, in this case, recommend, why don't you start with y? Y equals 0, 1, 2, 3, 4, 5. Look at the equations we're going to have to solve. If y is 0, we're going to be dealing with, sorry, this should be always in the frame. This is the law of the land. 3y minus x equals 4. So if we start with y, 3 times 0 is 0, minus x equals 4. Solve for x. 3 times 1 is 3, minus x equals 4. You see, you don't have to divide by stuff. If x is 2, 3 times 2 is, I'm sorry, if y is 2, if y is 2, 3 times y is 6, minus x equals 4. But it doesn't matter how, just come up with a pair of numbers that do work. Oh, you say 5, 3? Okay, I'm sorry, 5, 3. Okay, so 3 times 3 minus 5 is 4. So we found one. Good, 5, 3 works. Now start cramming them out, because I would say for a straight line, theoretically you need 2, but if you have 3 or 4, then if you make a mistake, it will stick out like a sore thumb. So 5, 3 is on the line. We're going to graph 3y minus x equals 4. And something like x equals 0, y equals 4 over 3 is, I use this for checking my picture. 4 over 3 is just not precise enough to graph, but I graph it using the nice points, and then I use the nasty points to check. All right, we're losing some more people. And if the order bothers, you can rewrite it as minus x plus 3y equals 4. This is, what was this? 5, 3. So minus 5 plus 3 times 3 is minus 5 plus 9, that's 4. Find other points on this line. Chop, chop. Are you telling me you cannot find two numbers that do this? I don't believe you. I'm glad you're back. The others are not talking to me. I was asking for a second point, and I told them you can swap it if the order bothers, but they're not sure if they're here. That's all right. That's all right. You're back. 3, 5. -3 plus 3 times 5 is 12, not 4. Right? So 3, 5 will not work. All right, tell me this. What if y happens to be 0? Solve for x in this equation when y is 0. Eight, 4. Okay. So -8 plus 3 times 4 is -8 plus 12. 8, 4 will work. 8, 4. 8 for x, 4 for y. 8, 4. Oh yeah, 8, 4. Come on, y is 0. What is x? Y is 0, x is 4. Y is 0, x is negative. See, it didn't fit. It's more like -4, right? Because what you get is minus x equals 4. So x is -4. That's why instead of a lot of computing, you want to compute plot. -4. I think more like it. And then you kind of know what to expect. But if you come up with y, in this particular case, you don't have to divide when you solve for x. Well, you might have to divide by -1. So I would say come up with a y, solve for x. How about y equals 1? It should be somewhere here, right? Y equals 1 is, if y is 1, x is, if y is 1, what is x? If y is 1, x is, come on, put y equals 1 into this. And then it's just going to be a linear equation in one variable and not a difficult one either. Y is 1, what is x? Y is 1, x is what? Okay, so if y is 1, 3 times 1 is 3, 3 minus x equals 4. I see where you got 7, but it's more like around 1, you see? I see -1, x is -1. Add x, subtract 3, and there it is. X has to be -1, so y is. And that is your pattern. Your pattern is, I never go to the left, so 3 to the right, 1 up. 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 The persistence of that pattern is what makes a straight line straight. There. And now every point on that line will work. Okay. Any questions? All right. So I want to talk about something fun now. We could do one more, but I think one person already got it, and I'm not sure about the other, where the others are. They're not talking to me. So I want to talk about something fun. Namely, I want to talk to you about construction. Construction in mathematics, that's a more specialized thing. It doesn't mean you build it from construction paper, even though the construction paper has the word construction in it. It's a very specific way of drawing things where you can use only two things. You can only use, so drawing, we can only use a straight edge and a compass. Now, a straight edge is a ruler without markings. So this is a ruler upside down. That's a straight edge. So you cannot measure out distances using markings. So it's a ruler without markings. All you can do really is to put a straight line through 2 points. A ruler without marks. So all you can do is straight lines. And with the compass, pretty much all you can do is circles. This is a compass here. You can buy one for like $3 in Walgreens or even a grocery store selling. Buy one, it's a fun stuff. So what it is, it has a needle part and a graphite part. And then you open it up to a certain distance, you stab the paper, and then you roll it around. It's going to be a little bit of a learning curve, and you can make circles. And you can open it up or close it down, and nothing else can you use. And then the question is, what kind of things can we draw using these things? And as it turns out, it's a very interesting little part, not just of geometry, but of algebra. Because if we say, okay, this is 1, now what numbers can you construct? That's a very interesting set. Really quite interesting. So I want to show you some construction stuff. Let's start with the perpendicular bisector. Now, anything that is given to you is going to be given as a picture, not as a number. So construct the perpendicular bisector of a given line segment. Now, I'm going to have to give you 2 definitions first, and then off we go having fun. So a circle is a set of points, is the set of all points in the plane equidistant, equally far from, to a fixed point. Well, you see, the way we got the circle is that we didn't open, or this thing did remain the same. And let me give you a surprising little definition about the perpendicular bisector. Basically, given a line segment, the perpendicular, that fixed point is the center of the circle. So the circle has to do with 1 point. This is more complicated because there are 2 points. And the perpendicular bisector, bisect means half, exactly half. You find a midpoint and you draw a perpendicular line. That's basically how we can describe it. But the defining property is the following. Anytime you pick a point on this line, these triangles are all going to be isosceles. You see they're all isosceles. And that is because the perpendicular bisector is a set very much like a circle. It's basically the set of all points equidistant from the 2 points. It's not a fixed distance. It could be far as long as it's equally far. So given a line segment, the perpendicular bisector, although it's perpendicular, that's not a defining property, is the set of all points in the plane equidistant to the endpoints of the line segment. Equidistant to A and B. All right. Now for some fun. So with construction, it's a procedure. You have to write down the steps, because even if you construct it, we just see the finite product. We don't see what happened first, then what else happens. So in a construction problem, you would be given a line segment like here. Now I want you to construct the perpendicular bisect. So here's what we're gonna do. We're gonna open up a compass to, we have to make sure that it's open up to more than half of the line segment. Well, actually I'm gonna make it more than half of the line segment there. And then we're gonna have to preserve this distance and put a circle centered around A and centered around B. Oops. Shaky hand. Centered around A, centered around B. It's very important that we didn't change the radius. So the radius is that equal this, I'm sure you know. And now look at this point. This point here is equally far from A and B because these two circles have the same radius, right? And so is this point. And guess what? 2 points uniquely determine a straight line. So that's how, but you have to sort of write it down, what I just explained in language, that you have to draw. Now, the problem, if your circle is too small, they don't meet, right? Circle here and a circle here will not, like that, is not going to help you. But if it's more than half, then there it is. Now, I want to show you a really cool website, which I'm going to post. It has little movies. Okay. So here is the basics. So here is the line segment bisector. These are the basics. And here is the video. I forgot to tell you something, but there it is. Yeah. This is one of the simplest things. And you can go again. So you can learn steps by watching. There are all kinds of videos here. Oh, I have to go back. So there are two basic things, and then points and lines, and all kinds of really interesting stuff here. So here is the thing. Usually a construction involves many steps. And you don't want the picture to be too crowded. So instead of what I drew, people are not drawing the whole circle, just the part we know we're going to use. So instead of this entire circle, I'm just going to do this part and that part because I know that's the only part I'm going to use. And this is one trick to keep your paper less busy. And that's why it was just drawing those silly little arcs instead of the whole thing. But those silly little arcs are basically part of these two circles that I actually drew out. All right, so that's our first lesson in construction. Any questions? All righty then, thank you guys, and I'll see you next week. Have a nice weekend. See you next week.